We are on Unit 2. This is Notes 1 of Unit 2. This section is on implicit differentiation. I'd like to begin by talking a little bit about our notation that we use for derivatives specifically. And can't really talk about that without telling you a little bit where this notation came from. There are two founders of calculus, Isaac Newton and Gottfried Leibniz, and we get our notation from Leibniz. Okay, and their simple reason is that he published what we know from calculus before Newton did. Okay, there was a lot of controversy back in the day when Leibniz published. Isaac Newton was upset about this because he had done a lot of work on it and he felt that Leibniz had plagiarized his work. It's thought now that they both developed the ideas behind calculus independently of each other, but since Leibniz published first, we get our notation from him. So there's that little blurb about that. So one of the notations, one of the ways that we notate the derivative is with this. It's written this way. It looks like a fraction. It's the derivative of y with respect to x, and that's how we would say that. Well, if I'm just saying it in an equation, I call this dy dx. That's what I call it. I don't call it dy over dx. I just call it dy dx, and that's pretty accepted. But if you want to call it dy over dx, I'm not going to be upset about that. But anyway, this is the derivative of y with respect to, I'm going to abbreviate with respect to WRT, that's with respect to x, all right? So let's say dh dt, t is a common independent variable, dh dt would be the derivative of h with respect to t, right? So it's this form of notation, it turns out that it is extremely convenient for us to use, okay? By the way, in dy dx, x is the independent variable. Okay, this is telling me that y is a function of x. H is a function of t. T is the independent variable. Okay. All right. Also, another way that we can denote derivative is by starting out just having what I would say in an equation. I would say d dx. This is d dx, and this means the derivative of something that would come after this, whether it's h or y or an expression, maybe sine x or whatever. This is just the derivative of what comes next with respect to x. Okay? d dt is the derivative with respect to t. Yeah, and so forth, and so on. Okay? So I could say, what is the derivative with respect to x of 5x cubed plus 7x minus 10? And for that derivative, I would use the power rule, and I would say, okay, the derivative of this expression is the derivative of each term, so that would be 15x squared plus 7 plus 0. So just 15x squared plus 7. The derivative with respect to x of x sine x. And I'm using these brackets. You could just, there's no reason to use brackets here. We could just use parentheses. Not sure why I chose brackets, but that's okay. For this derivative, we would need to use the product rule. So this is the product of two terms. So the derivative of x is 1 multiplied by sine x plus Now the derivative of sine x is cosine x, and then multiplied by x left alone, which we could rearrange or simplify that to sine x plus x cosine x. Okay. One more before we go on. I like to review a little bit. This time brackets would be more appropriate because I'm going to have parentheses inside here. So this is the derivative of cosine cubed of 5x squared. So this is a chain rule. In fact, it's a little bit of a more complicated chain rule because there's not just an x right here. The 3, this power of 3 makes it a chain rule, but also this 5x squared rather than just x makes it another chain rule. So taking this derivative is going to be a little bit tricky. So first of all, this power, I multiply it by the coefficient, so 3. Then I need to keep my cosine of 5x squared, but reduce the power by 1. So keep your cosine, reduce the power by 1, and we always keep that same argument of the trig function. Now I need the derivative of cosine of 5x squared. Well, the derivative of cosine of 5x squared is negative sine of 5x squared. And then lastly, we need the derivative of the inside, this 5x squared, so times 10x. Okay, so simplifying this a little bit, this would be negative 30x. Oh goodness, the phone was ringing and it messed me up. Negative 30x cosine squared 5x squared sine of 5x squared. And that would be that derivative. So let's just take a pause there. So that these are all things that we've already. Okay, so what we did here by taking these derivatives, I want to, this was a little bit of a review, yes, but in each of these expressions we had x's, right? And we were taking the derivative with respect to x, right? So each of them, it kind of made sense. We were taking the derivative with respect to x of an x expression. What if that's not the case? What if we try to take the derivative with respect to x of something that doesn't have x's in it, some function of x? What if we had like 4y cubed plus 7y squared minus 8y plus 1? Okay, how do you take the derivative with respect to x of not an x? That's where we need what is called implicit differentiation. So this is where we need implicit differentiation. So, okay, implicit differentiation is when you are taking the derivative of an expression with respect to some variable that is not in your term. Okay, all right. So that's where we're headed. That's what we need to be able to do here. So before I just tell you how to do it, let's talk about why we're going to do what we're going to do. So before we do, we started off talking about the notation that Leibniz gave us. I want to show you what one way that this notation is very convenient for us. So if I have dy, let's say I have dy dt, the derivative of y with respect to t, and if I multiplied that by the derivative of t with respect to x, I would get the derivative of y with respect to x. Okay, this notation conveniently lends itself to how we think of things reducing out. Okay, see how the dt's kind of reduce out? And then we would be left with dy dx. That's exactly one of the things that makes the notation very convenient. Okay, so this tells us that dy dx, if we're looking for dy dx and we have some other variables involved, that is equal to dy dt times dt dx. Okay, just writing it backwards. Okay, so what about this one? What about dy dx times dx dt? What would that be? Well, that would be these dx's, you can think of them canceling out. This would be dy dt. Therefore, dy dt must be dy dx times dx dt. Okay? Alright. You're thinking, what the heck, and what are we going to do with that? Well, let me show you. So we are looking for the derivative with respect to x of 4y cubed plus 7y squared minus 8y plus 1. We're looking for that, right? Okay. Well, I have y's instead of x's, so here's what I can do. I can take the derivative with respect to y, take the derivative with respect to y of that expression, and then I would multiply by dy dx. Okay. Do you agree that the derivative with respect to y times dy dx, the dy's would cancel and I'd be left with the derivative with respect to x of that, which is what I need. So go ahead, take the derivative with respect to y. That's something you can do, right? Take the derivative with respect to y. 12y squared plus 14y minus 8 plus 0, and then multiply that by dy dx. And that will be the derivative of this expression with respect to x. So let's think about what we just did. We went ahead and took the derivative with respect to y and then just multiply by dy dx. And that's what you're going to be doing. Okay? Let's take a look at another little example before we go on, before we look further at this. Let's say that we want to find the derivative with respect to x of secant y. So what would we do there? Well, we would go ahead and take the derivative with respect to y. The derivative of secant y with respect to y is secant y tangent y, and then you would multiply that by dy dx. This is implicit differentiation. Okay? So again, this part is d dy, and if you multiply by dy dx, then you get the derivative with respect to x. Okay? Alright. Let's look at the way you're going to see that. So let's look at some examples. Example 1, and in these examples, in these first examples, we're going to find dy dx each time. Okay? So in this first example, I have this equation, y cubed is equal to 5x cubed. Okay? Find dy dx. Well, this is not just a y equals, so I'm going to use implicit differentiation. You might be thinking, well, we could get this to be y equals by raising both sides to the 1/3. And yes, you can, but for the sake of showing you how to do this with implicit differentiation, I would like to do it with implicit differentiation, because sometimes you're not going to be able to easily, or you might not be able to solve for y. All right? So I'm going to take each side. Since I want dy dx, I'm going to take the derivative of both sides with respect to x. Take the derivative of both sides with respect to x. y with respect to x? Because the x is on the bottom right here. Okay. Now the derivative with respect to x of y cubed is 3y squared dy dx. Okay. The derivative with respect to x of 5x cubed is just 15x squared. If you really wanted to, you could say dx dx, but dx dx is just 1, right? So you don't have to write dx dx. But we could have been writing that the whole time, okay? Now we have this expression, all we have to do is to solve for dy dx. So I'm going to divide both sides by the 3y squared. This would be the safe stop answer. That would not be the multiple choice answer because they would reduce that 15 and 3 and make it 5x squared over y squared. Okay? Now, if you really wanted to, you could, solve this for y, put that in for y, but they're not going to do that. And as a multiple choice answer, it would look like that. Okay? All right, example 2. What if we have this? Y cubed plus y squared minus 5y minus x squared is equal to negative 4. Find dy dx. Well, I'm going to begin by coming in and taking the derivative of both sides with respect to x. Why with respect to x? Because of that x right there. If we were trying to find dy dt, then I would take the derivative with respect to t of both sides. Okay? So take the derivative of both sides with respect to x. And now I'm going to go, since this whole thing is not wise, I'm just going to go piece by piece. Okay? And whenever there's a y piece, I'm going to multiply by dy dx. So 3y squared dy dx plus 2y dy dx minus 5 dy dx minus 2x, no dy dx with that because there's no y involved there. And then this is equal to the derivative with respect to x of negative 4, so that's 0. Okay? Now we have to solve this for dy dx. So the terms with a dy dx, I'm going to factor out a dy dx from those terms. This negative 2x I'm going to take to the other side. And then just divide by what is with your dy dx. So dy dx is equal to 2x divided by 3y squared plus 2y minus 5. And that's it. If I'm not simplifying, I don't box, or I try not to box. I used to be a big boxer, but now I try not to box unless I'm simplifying an answer. All right, example 3. Let's see what I have next here. Okay, tangent x is equal to x times 1 plus sine of y. Okay, do you agree that it would not be real convenient to solve this for y? Just like up here, this would not have been convenient to solve that for y. This one, yeah, we could have solved that for y and found dy dx that way. But if we had, we wouldn't have gotten an answer with y in it. So it's a good thing that we did it implicitly. Anyway, okay, so we have this. I'm going to begin, we want dy dx, so we're going to take the derivative of both sides with respect to x. Okay, the derivative with respect to x of tangent x is just secant squared x. For this derivative, I need to use the product rule, right? Because we have x times 1 plus sine y. Those are my two terms in the product. So product rule, so the derivative of x with respect to x is just 1, multiply by the 1 plus sine y. I did not take the derivative of a y term, did I? So I do not multiply by dy dx. The only time you multiply by dy dx is if you took the derivative of a y term. Plus, now I'm leaving the x alone, and now I need the derivative of 1 plus sine y. Well, the derivative of 1 is 0. The derivative of sine y is cosine y times dy dx. Okay, be careful how you write that. I'm going to close my parentheses here so it doesn't look like just y is being multiplied by dy dx. The dy dx is being multiplied by the entire cosine y. Okay? Now we want to solve this for dy dx, so I take a look at it. I think I need to rewrite this a hair before I go on. Okay? So I'm going to subtract over the 1, subtract over the sine y, and then I'm going to divide everything by whatever's with the dy dx. So secant squared x minus 1 minus sine y would equal this thing, right? I guess I'll go ahead and write that. So dy dx is secant squared x minus 1 minus sine y all over x cosine y. Okay, and I'm going to say stop there. I do see a couple things I could do here to simplify using Pythagorean identity, but I don't think it's going to do a whole lot. If this was a multiple choice test, then, and if this was not one of the choices, then I would have to go and use some trig identities to try to figure it out. This secant squared x minus 1 would be tangent squared x. So I could replace that with tangent squared x, but I wouldn't do it unless I had to do it. Okay, example 4. Let's say we have 3y cubed plus 4xy squared plus 2x to the 4th is equal to 9x plus 11y, and we're finding dy dx. Okay? So, like we've been doing, if I'm finding dy dx and it's not a y equals, then I'm going to take each side and I'm going to take the derivative with respect to x of each side. I never seem to be able to leave myself any room in front of there, but anyway. Okay, so I'm going to go term by term, and whenever you are taking the derivative of a y term, we need to multiply by dy dx. So this first term, derivative with respect to y, dy dx. Okay, plus. Here I need a little product rule. I'm going to make this positive 4x times y squared is my next piece in the product. So product rule, derivative of 4x times y squared left alone. We did not take the derivative of y, so you do not write dy dx. You don't multiply by dy dx. Plus, now I'm leaving the 4x alone, and I need the derivative of y squared with respect to x. So that will be 2y dy dx. Okay, plus 8x to the 3rd, right, is equal to 9 plus, so what's the derivative of 11y with respect to x? 11 dy dx. Okay, I need to group all of my dy dx's together, so I'm going to move this 11 dy dx to the left-hand side. I'm going to move anything without a dy dx to the right-hand side, okay? And while I'm moving this guy over, I'm going to also factor out a dy dx. So I'm factoring out a dy dx from all of those terms. This 9y squared, here I'd have an 8xy positive. And this 11, when you bring it over, it's going to be a negative 11. And that will equal, okay, the 9 stayed here, so 9, minus 4y squared minus 8x cubed. And now just divide by what is with your dy dx. Okay. And I think that's it. All right. Example 5. Sheet of paper here. Okay, example 5. In this example, we're finding the derivative with respect to x at the point -1, -1. So this is another one that would be inconvenient to try to solve this for y. So let's just go ahead and get started. So we're going to take our equation. We're taking our equation and we're taking the derivative of both sides with respect to x, squeezing this in. So we're taking the derivative of both sides with respect to x. Okay, so for this expression, the derivative with respect to x, we need to apply the chain rule. So 3, keep your inside, reduce the power by 1, and then multiply by the derivative of the inside. Well, the derivative of the inside, we have the derivative of x, which is 1, plus the derivative of y with respect to x is 1 dy dx. Okay, and that will equal, okay, the derivative of x cubed with respect to x is 3x squared. The derivative of y cubed with respect to x is 3y squared dy dx. And the derivative of -6 with respect to x is 0. All right, so this is an expression with the derivative. We want to find dy dx at this point. So we have a choice right now. We could take this like we've been doing and solve this, do what it takes to solve this for dy dx. We could do that and then plug in -1, -1, or we can plug in -1, -1 now and then solve what remains for dy dx. I tend to prefer that method, but they're both good. They're both good. So whatever you do, you need to know this. When you plug in this point, you need to say what you're doing. Okay? We're communicating what we're doing. If I just went ahead right now, didn't say anything, and plugged in -1 for x and -1 for y all over the place, I would be implying that this line was equal to this line. And it's not. It's not all the time. It's only equal, they're only equivalent at that point. So say it. So I'm going to say at -1, -1, colon. Okay, that's all you got to do. Now you can go ahead and plug it in. Okay? If I don't see that though, again, you're telling me that two things are equivalent that are not equivalent all the time. All right, so I'm plugging in -1, -1, so I have 3 times -1 plus -1 is -2. Squared will be 4 times 1 plus dy dx is equal to 3 times -1 squared plus 3 times -1 squared dy dx. And now I have this to solve for dy dx, which is a little bit better. So this will be 12 plus 12 dy dx, distributing that 12 through, is equal to 3 plus 3 dy dx. I'm going to subtract 3 dy dx from both sides, and I'm going to subtract 12 from both sides. So dy dx is -1 at that point. Dy dx is not always -1. It's only -1 at that point. Well, it may be -1 at some other point as well, but it's not always -1. Okay? All right, so again, saying that, it's important. You will not get full credit if you don't tell me what you're doing. Okay? All right. Example 6, this is our last example, and it says given x squared minus y squared is equal to 36, find the second derivative of y with respect to x in terms of x and y. Okay? All right, well, we need the second derivative, so to get the second derivative, we need to first get the first derivative. So we're going to get the first derivative first. Okay? So I'm going to take my expression, take the derivative of both sides with respect to x, and on the left-hand side of the equal sign, I'm going to have 2x minus 2y dy dx. And then on the right-hand side, I'm going to have 0. Okay? Now, my advice to you is do not try to come in here and do this implicitly another time. Go ahead and solve this for dy dx right now. So dy dx, I'm subtracting the 2x over, and then I'm dividing by that negative 2y. So dy dx will be x over y. Okay? So that's the first derivative. Now we need the second derivative with respect to x still. Okay? So the second derivative, to do that, I'm going to come here. Let me rewrite this and give myself a little bit of space. I'm going to come down here, take the derivative of both sides with respect to x. Okay? So, the derivative of dy dx with respect to x is the second derivative. And now you might be able to see why we use this notation for the second derivative. Look visually. It looks like d times y, right? Which would be d squared y. Doesn't that notation look like that? Yes. So that's why we have that. On the bottom, this looks like dx times dx, which is dx squared. That's why we write dx squared here. So dx squared. So this means the second derivative with respect to x. That's what that is. Okay? All right. So over here, we need to employ the quotient rule, but we're taking our derivative with respect to x. So anytime we take the derivative of a y term, we need to multiply by dy dx. Okay? So first, start on top. Derivative of x is 1. Keep the bottom the same. So multiply by the bottom. Minus, now I'm going to keep the x the same and multiply by the derivative of the bottom. Well, the derivative of the bottom is 1 dy dx. All divided by the bottom squared. That's the quotient rule, right? Okay, this is the second derivative, but we were supposed to find the second derivative in terms of x and y. Did we find it in terms of x and y? Well, I see an x and I see y's, but I also see dy dx. So right now, it's in terms of x, y, and dy dx. We only want it in terms of x and y. So in place of dy dx, we need to put in there what dy dx is equal to. And dy dx is equal to x over y. So I'm going to plug x over y in for dy dx. So this is equal to y minus x times x over y all over y squared. Okay? This would be the safe stop answer, but this would not be the multiple choice answer. AP will very, very rarely, I can't think of a time when they left a multiple choice answer as a complex fraction. So they're going to do something to get rid of that. So we're going to multiply top and bottom by y, since y is our little denominator, and that would give us y squared, because y times y is y squared, minus, here the y's would cancel, we'd be left with x times x, x squared, all over y cubed. Okay? This is another kind of safe stop answer, but believe it or not, what if that's not one of your choices? Because I can see one more thing we can do with this. And it's something that you might not think to do. But this is something that they would probably do. Okay? In the very initial problem, we were given that x squared minus y squared is 36. We were given that in the initial problem. Look what we have in the numerator. We have y squared minus x squared. Well, x squared minus y squared is 36, right? So if I move the left to the right and the 36 to the left, I'd have negative 36 is equal to y squared minus x squared, right? So y squared minus x squared is equal to negative 36, and we know that because of the problem. So this would be the multiple choice answer. Actually, they would probably write it like this. So this would be the MC answer. Okay? Kind of tricky and kind of fun. All right. Time for you guys to try on your own.